Alright, so welcome back to particle physics and the standard model. This is lecture 38 and last time we saw what happened to fermion masses after electroweak symmetry breaking. One obvious thing that happened was that the Higgs field bequeathed a mass to the fermions because finally we were able to marry left handed and right handed spinors and you got all these various masses that were proportional to the Yukawas and the Higgs vacuum expectation value, right. And one more consequence was that the Higgs boson itself, the small h, now had its own Yukawa sector with couplings given by these quantities, right. This is proportional to the original Yukawas that we began with. But what was non-trivial was that to get to this mass basis, we had to rotate the Yukawa matrices, not the Yukawa matrices, we had to rotate the fermion fields in flavor space, right. Said differently, we had to diagonalize the Yukawa matrices such that we got diagonal masses, correct, in flavor space, right. We do not call an up when we put an up quark with a charm quark, we do not call that the up quark mass, right. We call it a mass only when it is up quark and an up quark. So we have to go to the diagonal basis, right. And we needed some matrices to rotate the fermion fields in flavor space, which also helped us diagonalize the matrix, and that is what we have written down here, right. Those happen to be unitary matrices. And the interesting consequence is that if you look at the W bosons interactions, then since the W bosons act only on left handed fields, when I go from the flavor basis to the mass basis, I cannot help picking up this LU dagger LD combination, okay. So it is a literal observable because you can actually switch your experiment, you can actually produce particles say in the flavor basis and detect them in the mass basis. So you will pick up this extra coupling. So it is an observable matrix of effective coupling constants known as the CKM matrix. And we wanted to parameterize the CKM matrix with degrees of freedom that are actually observable. And we saw that in general, since this is a unitary matrix, you could start with 9 real degrees of freedom, but then only some of them could be physical. And to see that, we said that those 9 should contain 3 rotation angles and 6 complex phases. And now we are in the process of eliminating some of the unobservable degrees of freedom, okay. So how did we start? We looked at some of the phase freedoms that we had in the mass sector, right. So if I can write on the mass term like this after symmetry breaking, and that would mean that I can always rephase the quarks in this manner. If I rephase the left handed quark with the same phase as the right handed quark, then I can eat up the new phase and I end up with an invariant mass Lagrangian, correct. So I had 6 such phases and it looks like I can eliminate all the 6 complex phases in the CKM matrix using this freedom. But let me show you why you can't really do that, okay. I am going to claim that if all alpha I were equal to beta I, okay. So if all the 6 phases were equal, okay, let me write it in words, all 6 phases equal, then you cannot remove it from the CKM matrix, it will have no effect in the CKM. Okay. If this is not clear already, let me actually illustrate it by actually writing out the CKM matrix this way, okay. So I am going to write out, so we have a VUD, right. I am going to pick 6 arbitrary elements where I give it a phase, okay, and I am going to write the phases in a funny way, okay. Let me call it e power I theta 1, okay, are we using theta? Yeah, let us just call it theta, but I am going to add, okay, I am going to call the entire phase, let us call it some phi, okay. And what else shall we pick? Let us pick VCD. Let us say VCD comes with its own phase, so let us call it e power I theta 2 plus phi. So, this is basically theta 1 plus phi, theta 2 plus phi, this is the entire phase, okay. And then let us pick one more random element, let us pick VCS. So, VCS is the third phase, okay, and then I will pick VUB. VUB is e power I theta 4 plus phi, and let me pick VCB. So, VCB is e power I theta phi plus phi, okay. And for the last phase I am just going to use, so let us use VTB, I am just going to put e power I phi, okay. I am doing this for a certain reason, alright. Then of course the other elements do not have a phase, so I will just write that down, so VUS, VTS, and finally what should this be? VTD, okay. So, these are the 6 phases I begin with in the CKM matrix, alright. Now imagine, can I remove the theta 1? Imagine I want to remove just the theta 1. So, what do I do? Remember that I have hit this matrix on the left with a U L dagger, U L dagger and C L dagger and T L dagger, right. And then on the right I have hit it with what? A D L and D and S L and a B L, right. Now I can absolutely remove theta 1 by refacing the UL, correct, with a reface UL basically as UL e power I theta 1, and then I can eat up this phase in the mass base. When I go back here, right, I can eat up that phase in the UR part in the mass Lagrangian, correct. So, similarly I can remove theta 2, theta 3, theta 4 and theta 5 appropriately. I can make use of this freedom, correct. So, let me just do that now. I have removed this, 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 this and this appropriately by picking some field or the other on the left or the right and refacing that particular field to remove those 5 phases. But now you can see that I am still stuck with e power I phi, right, and that is still sitting 1, 2, 3, 4, 5, 6 in 6 different places. So, if I try to remove it using one other field, then I have already made use of my freedom for the refacing. I cannot make use of it one more time, right. So, I cannot reface 6 different fields at the same time to get this. I can only do it one at a time, correct. That is what this freedom means. If I have already done the refacing, I have already made use of the freedom in the chiral symmetry, right. So, that tells you that I am still stuck with the phase in the CKM matrix, okay. So, the grand conclusion is that the CKM matrix, okay, in the final census contains 3 rotation angles and one face. Alright, and this lets people write the CKM matrix with the following parameterization. This is a very useful parameterization, helps you visualize exactly what is going on. I like this parameterization more than other parameterizations. It tells me that I can think of the CKM matrix as 3 rotations. Okay. This is something like a rotation around an x axis. There is no x or y axis here really, but it helps us visualize what is going on. Okay. And then there is another, I can multiply with another rotation matrix. So, I have this sin theta 1 3 minus sin theta 1 3, but the really beautiful thing here is that this is a place where I can put that face. Okay. See, this face I do not have to carry around in all the elements. I now know there is only one face, so might as well put it just once, okay, in just one of the matrices that we think of as rotation matrices. Okay. And finally, one can visualize a rotation around the third axis. Again, these are not real rotations, these are all rotations in flavor space basically, not in real space. Okay. So, when we put it this way, it helps us really understand how much the quark flavors mix with each other. Okay. For instance, since we can actually measure all the elements, we can also write the measurements in terms of the parameterizations. So, theta 1 2 turns out to be 13 degrees. Okay. Theta 2 3 turns out to be around 2.4 degrees. Theta 1 3 turns out to be around 0.2 degrees, and delta is around 69 degrees. Okay. What does this mean? It shows that these are all small rotations. That is, there is not too much of the down quark in the strange quark, there is not too much of the B quark in the down quark, and so on. Okay, when you switch bases from interaction to mass bases. Now, this phase right seems to be large, but it is not particularly large. Okay, we will soon see the extremely important physical significance of this phase. Okay, it is not large enough for something that we want. We will see what this means. Okay. This is one way to parameterize the CKM matrix. There is another very popular way to parameterize. It is called Wolfenstein parameterization due to Lincoln Wolfenstein, and that simply goes like this. So, there are many even among Wolfenstein parameterizations there are many orders to which you can keep terms, but for our purposes it helps to just keep terms up to this order, where you have this 1 minus lambda squared over 2 and keeping only terms up to cubic order. Okay. Lambda squared 1, and here I am neglecting the faces. Okay, so I am just taking the real part. What is the use of this parameterization? When you put it this way, there is only one parameter to think about, right, and that turns out to be 0.23. All right. So, if it is 0.23, then what does this tell you? It tells us that the diagonal elements are more or less 1, right. This is literally almost 1, right. The VTB is almost 1, whereas the others are also, sorry, the VTB is so close to 1 that we just write it as 1, okay, but the others are not that bad either, okay, the diagonal elements are almost 1. So, that shows you that there is not too much mixing going on among the flavors, all right, and the off diagonal elements are of order lambda, that again tells you there is not too much mixing going on because lambda is much smaller than 1. So, it is an order of magnitude smaller, factor of 5 smaller, right. And then when you look at terms like lambda cube, that tells you that there is again very little mixing between the up the bottom quark, basically the up and the bottom, that is an almost diagonal coupling in the W interactions and so on, okay. Now, there is something very interesting to notice in all this, which is that the phase that we wrote down, right, the phase term only arises if we have greater than or equal to 3 generations of fermions, okay. How do we know this and why is this interesting? We will see soon, okay, but let us see why it is interesting, we will see soon, but how do we know this? Let us see right now, okay. So, suppose you had only 2 generations, then how would we have done the counting, right? Then if it had been real, if the CK matrix, right, had been real, then I am looking at an O2 matrix, right. Then how many rotation angles do I have in an O2? I have 1 rotation angle, right. Agreed? So, it is just what? So, we write it as cos theta sin theta minus sin theta cos theta, right, that is what we would do if we had just 2 dimensions, correct, that is what this means. So, this is 1 rotation angle, okay. So, that would mean since the CK matrix would have been a 2 by 2 matrix and since it is unitary, I start with 4 degrees of freedom, okay, out of which 1 is a rotation angle and 3 are phases, complex phases, okay. But again this is what? This is a preliminary census, okay. Now, once again I have to go and use my chiral symmetry, right, but now I have 2 generations, correct, and that means instead of a u1 power 6 chiral symmetry, I make use of exactly this, but with 2 generations. I have freedom to rephase 4 fields. In other words, I have a, let me write it in the color I used before, I have a u1 power 4 chiral symmetry, okay. That just means I have 4 phases that can be absorbed essentially in the beginning at least, but I know that it is not 4, right. I know that one phase cannot be really absorbed, that is still fine, okay. One phase cannot be let me not write it that way actually. So there are 4 faces that um, can be absorbed. That now gives me lot more freedom to absorb the faces, right? It tells me that all 3 CKM, let me put 2 cross 2 just to remind you, faces can be removed. Agreed? So earlier I had 6 faces in the CKM, 6 that may be absorbed, but 1 was still a constraint. So I was still stuck with 1. But now I have 3 faces in the CKM, but 4 freedoms basically in my refacing. So I can easily, even if there is a constraint and even if one of them seems to get stuck, does not matter. I still have 3 freedoms left and I can remove all the 3 faces from the CKM matrix, right. So in the final census, again for 2 cross 2, right, I have just 1 rotation angle. Okay, and that is the angle known as the Cabibbo angle. This is what Cabibbo had realized. He had even worked out the refacings and all that. Okay, but then back then there were only 2 generations that were discovered. So he was a bit unlucky. He was kind of ahead of his time. He was using the experimental data available at his time, and that is the reason why he did not get a Nobel Prize. Okay. Okay, so here is what I am going to claim and show you how this comes about. Okay, the claim is that this e power I delta, right, when I have this unremovable phase in mass mixings like the CKM, that is exactly what gives rise to CP violation. Remember this from all those lectures ago? I had claimed, if you remember, in one of those early lectures, that as long as I have greater than or equal to 3 generations, I will have CP violation in the weak sector, right. This is where that comes from, okay, by looking at how you can reface fields and remove unobservable fields from the CKM matrix. Okay. What this still does not tell you is, why does a phase imply CP violation? That is still not clear, it is just a claim that I am making, right. So this we will explore in more glory in the next lecture. So here I will wrap up by writing down the Lagrangian in the mass basis now with the phases put in, okay, and then I will give you a hint for what to do to see the CP violation going on, but in the next lecture we will do it in full detail. Okay. So I am going to write that for some combination of I and j, okay, in the mass basis, my Lagrangian would contain some Vij, okay, and I am going to pick out the Vij that contains particularly the phase. So let us write this UL dagger sigma mu dlj, but now with an e power I delta. Now I write the Hermitian conjugate, what happens? I will have a W minus, then I will have a DLI dagger, right, and I still have this. Now the UL becomes, the UL dagger becomes UL, and most importantly the phase has now gone to a minus of itself. the e power item. Okay? Okay, good. So, the hint I am going to give you is you have to apply the C and the P operators on this, then see whether you get back the same Lagrangian. If you do not, then CP is violated. Agreed? So, for this you need to go look up what is a C operator and P operator also, but especially the C operator in quantum field theory. It is not the same as what we had in when we did our quantum mechanical, when we use quantum states and so on, right. That is not what it is here, it is a little more subtle, which I will introduce in the next lecture. So, I will leave you here and see you in the next lecture. Thank you so much.